Hello, welcome back to our online classes, and today we are going to look at reactions of alkenes. This is organic chemistry. Before we start looking at the reactions of alkenes, let's look at the basic of alkenes. Alkene is an organic compound. And what is organic compound? Organic compounds are chemical compounds in which carbon atom is covalently bonded to other atoms, for example, hydrogen atom, or we can have carbon bonded to oxygen, we can have carbon bonded to nitrogen, we can have carbon bonded to, let's say, phosphorus. So these are organic compounds. Let's put our focus on carbon bonded to hydrogen. When a carbon is bonded to hydrogen, we call this type of organic compound as hydrocarbon. Hydrocarbons. So hydrocarbons are compounds in which carbon is bonded to hydrogen atoms. Hydrocarbons can be classified into two classifications. One is saturated hydrocarbons, and another type is unsaturated hydrocarbon. When we talk of saturated hydrocarbons, in these hydrocarbons, there's a single bond between carbon and another carbon atom. So in this case, we can find carbon is singly bonded to another carbon atom. And example, we have alkenes as the functional groups. Example of alkenes, we can have, let's say, pentane, which has 5 carbons. When we talk of unsaturated hydrocarbons, in this type, we find carbon is bonded to another carbon using multiple bonds. And these multiple bonds can either be a carbon-carbon double bond, or it can be carbon-carbon but then triple bond. And sometimes we can also find a 6-membered ring which has a double bond, and this one we call a benzene. So these are examples of unsaturated hydrocarbons. Carbon-carbon double bond, this one gives us a functional group called alkenes. This is alkynes, and this one we call benzene, or the array benzenes. Now in alkenes, for example, we can have ethene, and this is where we are going to build our studies today. So we have seen that alkenes is an hydrocarbon in which carbon is doubly bonded to another carbon atom. So sometimes when we're doing nomenclature of alkenes, we need to consider the longest chain. Let's look at the nomenclature of alkenes. Now let's see, if we have carbon, we have double bond here, we have carbon CH2, let's say that we have them, the ethyl group CH3, and then we have H, and then we have CH3, and then we have CH2, we have CH3. So in case of the nomenclature of alkenes, we have said that you need to consider the longest chain first. The longest chain is going to give you the parent name of that alkene. For example, in this case, we can say 1, 2, 3, 4, 5. That's if we start from this methyl group. And if we start from this ethyl group, we have 1, 2, 3, 4, 5, 6. So it tells us that the longest chain here has 6 carbons, and because 6, we're going to use the prefix when we're naming, and 6 is going to be hexene. So now let's look at the double bond. Where is the double bond? The double bond must be located in a way that is going to give you the least possible number. So if we start from left going to the right, we have 1, 2, 3. So our double bond is on carbon number 3. And if we go to the left, we start from right, 1, 2, 3. It also in carbon number 3. So let's see. So from there, we have seen that our double bond is on carbon number 3. But then let's look at this substituent. This substituent is on carbon number 4 if we're moving this way, but if we're moving to the right, it is on carbon number 3. So if you look at 3 and 4, you realize that 3 is the lowest number, and therefore we are going to name this compound going to the right. So our substituent is on carbon number 3, and our substituent is a methyl, so it is 3-methyl, and our double bond is on carbon number 3, then we can say 3, so we can combine this to give us the real name of this structure. So that's going to give us 3-methyl, 3-methyl, 3-hexene. This 3-methyl tell us that this methyl substituent is on carbon number 3, and also this 3 tell us that the double bond is on carbon number 3. So this is how you can do the nomenclature when it comes to alkenes. Now let's look on the names. Sometimes you can realize that on the carbon-carbon double bond, or on the carbon of the double bond, you have 2 alkyl groups. Okay, you can have 2 alkyl groups. For example, you have CH3 bonded to this carbon, and we have a double bond here, and on this side we have, let's say, an ethyl group, and this is H and this is H. So how many carbons here? 1, 2, 3, 4, 5. So this is going to give us pentene. Okay, now sometimes, for example, in the cases that you have seen here, we have 2 types of alkenes. We can have an alkene, for example, in which carbon double bond is on the carbon number 1, number 2, and number 3. So sometimes you can find this double bond is on carbon number 1, and this is what we call terminal. This is what we call terminal alkene. Sometimes our carbon-carbon double bond can be in between the other carbons, and this is what we call internal alkene. Okay, now sometimes when you are naming, or in the nomenclature, when you are naming these alkenes, you may realize that you have 2 alkyl groups on the sides of the double bond. So when you have 2 alkyl groups, then we have to introduce other names that we are using during the naming, and one of them is cis and trans. So when do we use cis and when do we use trans? We use cis now when the alkyl groups are on the same side, or the alkyl groups with the highest priority are on the same side of the carbon-carbon double bond. Okay, now let's look. If we take this carbon number 2, here we have priority number 1, methyl, as priority number 1 compared to hydrogen on this carbon. And if we look carbon number 3, we have ethyl group, which has the higher priority compared to this hydrogen. So you can see that on the same side of the bond, or on the same side of the double bond, we have the alkyl groups. The 2 alkyl groups are sitting on the same side, and that's going to give us what we call cis. So when we're naming this, so 1, 2, 3, 4, 5, then we can say cis, double bond is on carbon number 2, and then we can say cis 2 pentene, cis 2 pentene. Now if it happens that now instead of having this on the same side, then we can have them on opposite side. Let's swap, such that on this side now we are going to have CH2 and CH3, and on this side we are going to have hydrogen. So you can see now on this carbon we still have methyl as the first priority, and we have hydrogen as the second priority on this carbon. But if you consider this carbon, on the carbon number 3 on the upper side, we have hydrogen, and on the downer side we have the ethyl group. So ethyl group as the first priority, so we are going to give it number 1, and then hydrogen is number 2. So you can see that in the same molecule, now the higher priority groups are opposite each other, and when they're opposite each other we say trans. Trans means opposite. So in this case we can then, when we are referring to this one second scenario, we can then say trans 2 pentene. So this is how we can name alkenes when they have 2 alkyl groups. We use cis and trans. Now let's look. Sometimes we can have 3 or 4 alkyl groups on the carbon or on the parent chain of the carbon. For example, if we have C carbon double bond, and then let's say we have C, the ethyl group, and then we have the methyl here, and then we have, and then let's say this side we have hydrogen. So you can see that on this carbon-carbon double bond we have 3 alkyl groups. So in terms of numbering, this is going to be number 1, number 2, number 3, number 4, number 5. So we still have our pentene. Now if you look, now you realize that when you have 3 or 4 alkyl groups on carbon-carbon double bond, then we can also use the other names like E and Z. So when do you use E and when do we use Z? Now what you need to do is to divide this double bond into 2 halves and then look at the carbons on each side of the double bond. Now if we look carbon on the left, this carbon here, you can realize that this is the first priority, okay, 1, and this is the second priority, okay. And if we look this carbon number 3, we have this priority number 1 and this is number 2. So now you can see that on this carbon we have the ethyl groups on the top and the methyl groups down here. So now if you look, you realize that the higher priority are on the same side, okay, on the top side or on the same side. So we have number 1 and number 1, and on the donor side we have number 2. So in this case we are finding that the first priority or the higher priority are on the same side, and this is going to give us what we call Z. In this case we realize that the two sides, the higher priorities are on the same side, and when they are on the same sides then we can use Z, and in this case we're gonna say 2Z, and our methyl group is on carbon number 3, 3 methyl, 3 methyl, 3 methyl, 2 pentene. And when we swap now, let's swap and let's say this side is now methyl group and this side now we have the ethyl group. So when we have now ethyl groups coming down, this is going to be our first priority and this is going to be our second priority. Compared to this, now we have first priority and the second priority sitting on the same side, leaving also this side second priority and first priority sitting on the same side. So you can see that the first priority on both carbons are opposite each other, and that one gives us what we call E. Okay, these are all German words, so E means opposite in this case, and we are going to have our 2E, then 3 methyl, 3 methyl, then others follows. So this is how you can do the nomenclature. More often you use cis and trans when you have 2 alkyl substituents on the carbon-carbon double bond, and when you're using E or Z when you have 3 or 4 alkyl substituents on that carbon of the double bond. Fair enough? So now, having known that, let's now start our reactions of alkenes. When we are talking of hydrohalogenation reactions, is the additions of hydrogen halide to the carbon-carbon double bond. Remember, this is how our alkenes looks like. So when we do this, or when we perform this step of the reaction, hydrohalogenation is the electrophilic addition, or it is the addition of hydrogen halide to the carbon-carbon double bond or to the alkene. So when this happens, this X can be any halogen, it can be chlorine, and it can be bromine. So let's say then this is our carbon, and we're adding, let's say in the case of chlorine. Now what happens in this case, and let's look at it in terms of mechanism. So when we're doing hydrohalogenation, the first thing is going to happen is the addition of the electrophile to the carbon-carbon double bond, and that's the first step. This hydrogen here is going to be added to the carbon-carbon double bond, and for it to to go this side, what is going to happen? It means that this bond here, the hydrogen chlorine bond, must be broken. Chlorine is more electronegative than hydrogen, and therefore when this hydrogen chlorine bond is breaking up, it is going to break up heterolytically. Heterolytically means that during the breakup, chlorine will take all the electrons, because one bond gives us 2 electrons. So all the electrons are going to go to the chlorine, and this is going to leave our hydrogen electron deficient or deficit in electrons, which is going to make it electrophile. Electrophile meaning that it has less electrons. While we are going to have our chlorine atom is now nucleophile because it has 2 more electrons. So this is how our chlorine looks like: 4, 5, 6, 7, 8, and together with the new 2 electrons that it has gained. So now this bond here will be broken, because during reaction some bonds are broken and some bonds are formed, like hydrogen chlorine bond is being broken. So now this bond will break up and attack this electrophile, because now the carbon-carbon double bond, the double bond will donate electron to the electrophile. This double bond acts as a nucleophile. It has more electrons, and therefore it will donate it to our electrophile proton, and that's going to cause this bond to be broken, and that's going to lead us to what we call a carbocation. So we are going to remain with this one bond and with this hydrogen. So this was the hydrogen, this was the hydrogen. For example, if we're talking in terms of ethene, and this is going to be our new bond. So our new bond is formed here. So that's the formation of the new bond between carbon and hydrogen. Now when this bond is broken, it leaves this carbon here to be carbon deficit. Instead of having 8 electrons, now it has 6 electrons. So this carbon here is acting as an electrophile. So this carbon now acts as electrophile because it has less electrons. So what happens then? Our chlorine or chloride atom, which had gained 2 electrons extra, is now going to donate those 2 electrons to our carbon, to this carbon here, because this carbon has formed what is called carbocation. So this bond or these atoms will be donated to this carbon here to form new carbon chlorine bond. Okay, so the arrow is going this side, and the direction of the arrow is very important. So this is going to give us this. So we are going to have carbon, I'm going to have hydrogen, we are going to have hydrogen. Well, let me just rub it quick. So we are going to have this one, the new bond that we have formed here, and then initially also we have hydrogen here, we have hydrogen here, and then we have our chlorine atom. Now this is how hydrohalogenation takes place. Now there are things that you need to know in hydrohalogenation. In this case, you find that the chlorine is adding to this carbon. Why? Because all this carbon or the second carbon is having only hydrogens. Sometimes, if this carbon, let's say, is substituted, then we are going to look at the behavior of hydrohalogenations. Its behavior is in the sense that it is regioselective. Regioselective means that this halogen will go to the more substituted carbon, and the hydrogen will go to the less substituted carbon. Less substituted carbon means that that carbon has high number of hydrogens, and that follows what we call Markovnikov's rule. So for example, if then we have carbon, and let's say we have methyl in this group, and we have H, and we have H, and we are reacting this with, let's say, HBr. So this bond will break, and now we know. So in that case, we can form carbocation. Here is CH3. We can form carbocation on this carbon, and we can also form carbocation on this carbon. So This can give us CH3 bonded to this carbon, and this is going to give us also Br plus C, bonded to C, and it can also give us CH3 bonded to C carbon to this carbon, and this is Br, right? However, this is wrong because it follows Markovnikov rules, which say that the halogen will be bonded to the most substituted carbon of the double bond. If you look at this carbon, on this carbon here, if this is number 1, number 2, number 3, carbon number 3 is bonded to the methyl group, so it has one substituent, while this carbon does not have any substituent, it has only hydrogen. So this is our right answer, or the right product. And sometimes you can find that, now let me just wrap quickly. You see, sometimes you can be given, for example, to give the products of the following. Let's say now you have something like this, okay, and you have been given HBr, okay, HBr. So you know automatically in this case we're just going to have our Br, okay. But if, let's say, now we have changed, now we have put methyl substituent here plus HBr, so our product is going to give us, remember, Br go to the most substituted, so this is our Br and this is our methyl group. So this is the right product. Now sometimes rearrangement can take place, and therefore, for example, in case whereby we have, let's say something like this. So this is the tertiary carbon, because this is a methyl, so this tetbutyl that forms on this. So we expect carbocation to be formed on this carbon, here. That is where we expect it to have a lot, or the major product, because in this carbon here, this is carbon number 1, number 2, number 3, so number 4 you can choose, is this one or this one. So we expect our product to be formed on this carbon number 2, because carbon number 2 has the highest number of substituent. But you realize that when the carbocation is formed here, there can be a shift of this methyl group to come this side, so that we can have something like this. So now we have the methyl leaving a carbocation forming on this third carbon, and that is when now our bromine can come in now and then go to this carbon, giving us this product here. So this is our Br, this is our methyl. So hydration reaction is the addition of water to alkenes to form alcohol, and this occurs in the presence of a strong acid. For example of the strong acid that we can use sulfuric acid, SO, sulfuric acid, or we can use hydronium. Okay, this is an acid. Why are we using acids when we're performing hydration? This is because the water that you are adding to the double bond is too weak to activate or to protonate the double bond itself. So we need something that is going to activate the double bond so that we can add water perfectly. Okay, so this is what happens. So if this case, this is the carbon double bond, and then we have water. Sorry, we are going to add water, but we add it in the presence of hydronium. So this is our H, and this is our H2, and that is our 2 plus 1, 2, 3, 4, 5, 6, 7, 8, and then this is the hydronium. Step which is going to take place is the protonation of this carbon-carbon double bond, and that will happen because the hydrogen, this bond here, will break so that it becomes partially positive, and then this is what is going to happen. So we have already protonated this carbon-carbon double bond, and that's going to give us carbon-carbon, but this carbon is going to have carbocation. Remember, because this is a carbocation carbon, or it's going to form carbocation because when this happens, these two electrons are going to move to form a new carbon hydrogen bond, leaving this one with 6 electrons. So in this side now we have our OH, 2, 1, 2, 3, 4. Fair enough. So what now happened is that this water molecule is going to attract this carbocation to form new carbon oxygen bond. So this was going to happen, and then we are going to have, we have carbon now, carbon, so we still have our H here, and then we have our carbon OH, and then how many hydrogen do we have? We have 2. We have 2, and because it lost these 2 electrons there, so we have positive, and also we have also those 2 electrons. So this is what we have. Now once we have this, then we can deprotonate this proton so that we can form our alcohol. Deprotonate it to form an alcohol. So we have our H2 and we have our, and then this bond will be broken and we'll have to regenerate the acid that we used in first step. So this is our first step, second step, and this is our third step. So when this happens, we are going to regenerate on this, going to give us, let me write it here, we're going to have C, or let me grab it. So we're going to have carbon, but we have our hydrogen here, and we have now our oxygen, we have formed our alcohol, and then plus our hydronium acid. So this is how it takes place, or this is how hydration reaction occurs. Is the addition of halogens to alkenes to form what we call, or what we refer to, vicinal dihalide. So in vicinal dihalide occurs when the 2 adjacent carbons of the double bonds are bonded to halogens. So it means that these halogens that we are going to add are going to be bonded to the adjacent carbons of the double bond. So our carbon double bond plus halogen is going to give us carbon, but on these adjacent carbons we are going to have the halogens. So let's take, in this case, for example, if we have our, okay, let's say this is our X, and then we do halogenation, is going to give us this X and also this X. This X is halogens, can be bromine and chlorine, but we realize that because it's going to give us anti-addition, so that's the stereochemistry is anti-addition, so it means that we are going to have 2 products. So in this case, then let's take a real product or a real reagent. So we have double bond, then we add it to chlorine. Okay, so one of the product is going to give us, as one of the product in was going to form anti-addition. So we are going to have chlorine, and also we can have chlorine plus, in one case we are going to have chlorine, and we are going to have chlorine. So this is how halogenation of alkenes take place. Fair enough. It's very straightforward. You have to form, because it forms 50-50, which is a racemic mixture, so you need to show the stereochemistry. Okay, allohydrin is the treatment of alkenes with halogens and water. So it means that in allohydrin we are going to react alkene with halogen, and then we react it with water. So if we have our alkene, for example, then we react it with halogen, and then we react with water to give us a product. So the treatment or a reactions which involves treatment of alkene with halogens and water, that's what we call allohydrine. Allohydrines give us anti-addition. For example, if you have carbon-carbon double bond, then we react it in the presence of halogen and water, so our product is going to form, so this is going to be our X and this is going to be our OH. Okay, so let's look at the real example whereby now we have our chlorine and we have water, so it's going to give us chlorine and OH. So but we have said that is anti-addition, so let's show the stereochemistry. So it means that we are going to have, so let's say chlorine OH plus, we just change the stereochemistry, chlorine OH. So this is the products of allohydrine. Hydroboration oxidation reactions of alkenes is when we convert alkenes into alcohols. And how does this happen? The first thing that we need to do is to convert the alkenes into alkyl borane. So if we have a double bond, we can add BH3 so that we perform or we get what is called alkyl borane. So the first thing we need to do is the hydroboration, which is the first step. Hydroboration is the addition of borane to a double bond to form alkyl borane, and our alkyl borane is going to be C carbon, and then we are going to have BH2. So this is what we call alkyl borane. So this we have our HS, Now after this is when we can do oxidation, and once we do oxidation, let's say hydrogen peroxide or peroxide, so we can perform oxidation, and when we're performing oxidation, then the OH is going to replace BH. So we are going to have, when we perform oxidation, we are going to have our OH. So we have converted this alkene into this alcohol through a process called hydroboration oxidation. In hydroboration oxidation is the process in which we can convert an alkene to an alcohol through alkyl borane. So the first thing that we need to do is to perform hydroboration, which is the addition of borane to a carbon-carbon double bond to form alkyl borane. Once we have formed alkyl borane, then we can perform oxidation in which the OH is going to replace the BH or the B bond, so that we can form a new CO bond to form an alcohol. Remember, this thing is radioselective, and in case whereby you have other substituents on the carbon-carbon double bond, then BH will go to the least substituted alkene, the least substituted carbon, and then it means that our final product, which is the alcohol, is going to be formed on the least substituted carbon. So it means that hydroboration oxidation of alkenes is anti-Markovnikov's. Then, for example, in real life, let's do it in real life. We have a double bond and we have CH3, and then we have BH3, and then in second step we perform oxidation, and this is going to give us a product. Okay, and we have said that it is anti-Markovnikov, so it means that this our CH3 is still going to be there, and then this our OH is going to be formed here. So this is how hydroboration oxidation reactions takes place. Thank you so much for watching. See you next time. Hey, remember to subscribe and share with your friends so that each and every time we upload videos like this, you get notified. Thank you for watching. Welcome.